Hello again, Liam. All right, I'm seeing some of our friends on Facebook starting to rejoin here. Sorry for that technical difficulty. It seems like our feed from Zoom into Facebook went dead for just a moment there, but I think we're back. We'll give a couple more friends a few minutes to join in. If you weren't here at the very beginning of our program when we got started today, today we are talking about candy chemistry. So we'll be going through some candy chemistry and maybe some other Easter related chemistry or science experiments that you can try at home this weekend yourself. So we're seeing lots of our friends starting to join back up. Hello, everyone. If you missed it at the beginning, very, very sorry for our technical difficulty there. It looks like we're back up and running. Everything should be good to go for the rest of our program. And thankfully, I actually never even started our first experiment, so you haven't missed anything. Don't worry. All right. Lots of familiar faces in the chat. If you haven't done so already, please introduce yourself in the chat feature there. I see lots of returning faces, friends who join us every day for Echo Live. That's so exciting. We're so happy to have you. Thank you to our friends in Zoom for waiting so patiently while we got our other stream back up and running. Thank you very much. You guys are awesome. All right, so let's switch back over to our original experiment here, our first experiment, which is creating our candy rainbow using some Skittles. Now, we mentioned that you could recreate this at home using any sort of candy that has a colorful sugar coating on it. So we've mentioned that you could use M&Ms, you could use Skittles, possibly even jelly beans. If you would like to turn this into an experiment at home, right, that is a variable that you could change. That's one piece of this experiment that you could change, and then just follow the same procedure that we're going to move through together. So I've got my warm water ready to go. And again, we'll be pouring this just into the center of the dish. So we don't want to pour it on top of our Skittles directly. We want to let diffusion do the work here. And we'll talk a little bit more about what diffusion means once we get our Skittles nice and covered in water. So I'm pouring it in there very, very gently. And again, just enough to cover the top of our Skittles. And then we very, very quickly begin to see a pretty cool effect. So we really are creating that rainbow. Again, it took a few minutes of me arranging our Skittles in this particular order before the program so that we can create this rainbow, right? So the rainbow is created because of the arrangement, right? So we've got two different interesting things going on here. Number one, right, we see the color starting to come off of the Skittles and start to color the water. That is because of diffusion. Diffusion is the property of molecules to move from an area of high concentration, where there's a lot of something, to an area of low concentration, where there's not as much of something. So we see that happening as the Skittles, or as the sugar coating, starts to dissolve off of our Skittles. So right where they dissolve off of the Skittles, right, that's an area of high concentration. So we've got a high concentration of sugar right near our Skittles as that sugar starts to dissolve into the water. But that sugar wants to spread out, right? It wants to move into those areas of lower concentration. And so they start to spread across the plate to fill the water in the center that doesn't have any sugar in it. Now, you'll also notice that we have these streaks of color, right? So instead of immediately turning the water kind of a muddy brown color, we're actually seeing the color start to kind of spread out but stay with its own color. That's also because of density. So if we think about these sugar coatings, right, they want to spread out into the water, but the green dye is just as dense as the purple dye, which is just as dense as the red dye, which is just as dense as the yellow dye. So even though our eyes observe them as different colors, they don't really want to mix with each other because they have the same density. There's no way for them to move between an area of high and low concentration since they have the same density. Now, I did mention that this experiment is safe to eat after. And so you'll notice that if we shake them up, right, we can speed up that process of diffusion. We know that if we mix our red, orange, yellow, green, and purple, we get this kind of icky brown kind of color. But you'll also notice that inside the water, there are some of these white flecks floating around. Now, that's not gross. Those are actually the S's that just came off the Skittles. So they actually print those S's in a non-water soluble ink. It's an edible ink, kind of like they use for those fancy birthday cakes. But those S's are edible, but they will not dissolve in water. And so you can actually try to kind of scoop out some of those S's and see if you can grab them. It takes a little bit of practice, but again, we said as long as you wash your hands before your program, just like I did, this experiment is safe to eat. Now, I would strain the water unless you're kind of adventurous and you maybe want to see what it tastes like. Maybe it tastes good. I've never actually tried it, so I don't really know. But it is food safe. It's just water with Skittles, so it's kind of sugary water, which you could try drinking, I suppose. But the Skittles, even though they've lost their color, are still Skittles. And so you can play maybe a guessing game of what color did they used to be, even without their colorful sugar coating. So each color Skittle is a different flavor. Now that we've dissolved it off, they're all white. And all we've left inside is that non-water soluble sugary part of the polymer. And you could eat them. And so you could play kind of a fun guessing game with those. So you don't actually need to waste any candy with this experiment because it's one that you can eat afterwards. I'm seeing a couple people telling me that they would not eat these, like Michelle, and you don't have to, right? Maybe you have a brave soul in your home that is willing to play that guessing game with you, which could be kind of fun. I see that Elena tells me anything for Skittles, and I feel the same way. I'm going to eat these after the program after I rinse them off. I'm not really interested in the sugar water, but I am kind of interested in the mystery Skittles. All right, so we've done an experiment with candy that you might be getting, but I also wanted to give you kind of a recipe for a candy that you could make at home. This candy is made out of a polymer, and we've talked a little bit about polymers throughout Echo Live as we've gone through. So if you've ever made slime, that's a polymer. But slime isn't necessarily edible. Depending on what you make it out of, we normally make it out of a solution of glue and borax, which creates a polymer, which is a long chain of molecules all linked together, right? So we can create an edible polymer using gelatin. So gelatin is also a polymer. So I've got a recipe here. I've got the ingredients that I used to create something kind of fun, which you can very, very easily recreate at home with only a few ingredients. So for this, I chose a lime gelatin or a lime jello, and then I bought an extra pack of unflavored gelatin. And what I've done is I've actually made this gelatin according to the directions, used the extra gelatin to thicken up our gelatin, make it really hold its shape. And then I've actually poured it through these straws here inside this mug. This is my dad's favorite mug, in case you were wondering. If you need someone who will golf for food, he's your guy. So I've put my straws down here inside the gelatin. And so I've let them set overnight after I made my gelatin. I've set them down inside, and we just need to wiggle them out. Again, this cup is now full of Jell-O, which is still totally edible. So we'll just set that to the side, and I'll probably eat that with a spoon later. So what better weekend, right? Everyone deserves a treat. We've all been home for a while. And here's a treat that you can actually make yourself. So I rubber banded these bendy straws together, and I've actually used this gelatin to create my very own gummy worms. So I'll switch my camera over here, and I'll show you how, once you make your gummy worms, how you actually get them out of the straws, and we'll show you what they look like. So if you have seen bendy straws before, you know that they have this little bendy kind of crinkled up part on them. And so that's actually what's going to make it look like a worm here. So you only just need to pinch it pretty hard on the side where there's air trapped inside the straw, and then push that air through. And out the other end comes a gummy worm, right? Now I cut my straws in half so that I could make more with the bendy straws that I already had at home. If you have any sort of straws at home, they don't have to be bendy straws. They just won't have that little zigzaggedy part of your gummy worms here. But these taste really, really delicious, and they were really easy to make. Again, they're just made out of that gelatin. So here's just a regular straw, so not a bendy straw. And you can create your own pile of gummy worms at home. So very, very easy. All of these recipes and experiment guides are going to be posted on the Michigan Science Center's website today. Actually, they're already there. So go to the Michigan Science Center's website and search for at-home science if you're interested in a recipe or an experiment guide for any of the things that we're trying here on air today. So we've got a whole lot more gummy worms for me to kind of extract from their tubes a little bit later on. But let's move on to our next science experiment. So this experiment, if you'd like to try it at home, does require a bit of parent supervision. So for this next experiment, we are going to be using matches or birthday candles, whichever you might have at home. in order to pull a hard-boiled egg into a glass container. So if I go ahead and set my egg on here right now, we'll notice that it doesn't quite fit. If I were to try to jam it in there right, I would probably break the egg. I've gone ahead and I've already peeled the egg before the program. And so we know it's pretty soft and it's pretty malleable, right? But we don't want to push it in with our hand. We want to use science in order to do that. Ooh, someone wants to see the big straw. We'll use this one in just a moment. And so we're going to be using the same process of diffusion or tying it to air pressure. So if we think about what we learned about air pressure before, or what we've just said about diffusion when it came to the sugar in our Skittles, right? We said that molecules will always move from an area of high pressure, like this zone right here, where we've got lots of molecules packed really, really close together, to an area of low pressure, where there's no molecules. And over time, you'll create an equal amount of molecules in both of those spaces. This works with air pressure as well. We've talked about this a little bit when we talked about the Bernoulli principle, that areas of high pressure, right, want to fill those areas of low pressure air. So high pressure where there's lots of stuff or lots of air, to areas of low pressure where there's less stuff or less air. Now, we've also related this to temperature in the past. We've talked about how when molecules get warmer, they start to expand to fill up more space. But if we cool them back down, right, they contract. They start to take up less space, leaving behind kind of an empty space or a vacuum around them. Now, we learned about how we can actually create a vacuum using fire, and that's how we are going to accomplish this goal today. So on my tray, I have one hard-boiled egg that I've already peeled. I have an extra one just in case we need it. This one is not peeled just yet. I have some birthday candles here, so you could easily do this experiment with birthday candles. I also have matches, and we're just going to be creating a vacuum inside the jar and hope that that force is enough to pull our hard-boiled egg inside our flask here. Now, if you don't have a flask at home, that's okay too. Any sort of glass container will work. Now, you won't want to use plastic for this, right? Because we're going to be putting a small fire inside the container. Glass can withstand that fire. Plastic will melt. And so that's not ideal for what we're trying to do in this experiment. All right, so the trick is to light a match, let it start to burn. That way it doesn't immediately go out. Let's see, just like that one did. Light our next match. And we really want the stick to start burning here. So we'll tilt it downward, and then we're just going to gently drop our match down inside, and that one went out too. Now, here we go, guys. In science, right? We never give up. Maybe I need to be a little more gentle as I drop my match inside. Really get the wood starting to burn. Drop our match down inside, and then quickly place our egg over the lid of the container and watch what happens to the egg. It very, very quickly just squeezed its way right through the opening, falling inside our glass container. Now, if you look at my egg, you'll notice it's got kind of some burn marks on it from where it touched those matches. So maybe save this for an egg that accidentally falls on the ground, or make sure that you're okay with wasting one, because you definitely won't want to eat this one after this experiment. All right, so let's talk about what just happened though, right? As we removed the air from inside using our combustion reaction, right, or we also expanded the molecules inside, right? So as that air got warmer, those molecules started to expand, but we also started to use up some of the oxygen inside the container. Once the air molecules cooled back down, right, they contract. They take up less space than they originally did, and that area of low pressure, right, was almost like a vacuum, which pulled the egg in. Outside the jar, we didn't change anything, right? There's lots of air outside the jar that was ready to act as that area of high pressure or high concentration. That high pressure zone wanted to push in, and it actually took the egg with it. Now, the tricky part with this, right, is how do you get the egg out of the container? So say you used a container that you do want to keep. I recommend maybe not using a container that you want to keep, but since this is a hard-boiled egg, right, we could, in theory, just take something long like a wooden spoon and we could just mash it up, right? And we could probably get the egg out in pieces, but that wouldn't be any fun at all, right? So if we want to get the egg out whole, what do you think we should do? Tell me in the chat. Do you think there's a way that we could use the same principle of high pressure and low pressure zones in order to get the egg back out of the container hole? Tell me what you think. While you think about that, while you send in your answers here, I'm just going to try to get just the pieces of the match out. So not our egg, we'll leave the egg inside for now. We'll try to get just our pieces of the match out and think about that experiment. Think about how we tied this to air pressure and how could we manipulate the air. Taking a look through our comments here. Some great question. All right, now, I did see a question about why did I use my dad's favorite mug? Because I didn't do anything to it. He'll get it back, I promise. But my dad has been helping me with a lot of our science experiments here. He loves science, and so I know he wouldn't have minded. And it was just the perfect container for the height of my straws, just to fill them almost to the top while also leaving just that small pocket of air so that we can squeeze those gummy worms out of the tube. So I'm seeing some great suggestions. Someone suggested that I turn it upside down, right? And maybe gravity could do the work, but that's not necessarily working. Even if I shake it pretty hard here, it's not necessarily falling out, but I see a couple people combining that step with something else. We could put the fire under the egg, right? But the room that I'm standing in is pretty large. So without another container that I could seal, right, to create that low pressure zone, I can't really create a low pressure zone here in my basement. That would require a pretty big fire and that would be pretty dangerous. But we can use air pressure in a different way, but you're on the right track. We need to create an area of high pressure inside the glass this time. So we need the area of high pressure to be inside instead of outside, which will reverse this process. So I'm seeing some great suggestions, but this one's pretty simple. It takes a little bit of practice and it doesn't always work, but I'm gonna try my best. All we really need to do is create that area of high pressure, and you can do that using your own air that's inside your body. So I'm just going to blow air inside the jug while keeping the egg upside down, keeping the egg just like this, so that that area of high pressure will then start to push back down on the egg and push the egg out. So let's see what happens. Ta-da! Right, so just using that principle of high pressure zones, we did get the egg back out of the jar, completely intact, unharmed completely. So great suggestions, you guys. You were exactly right. Create that area of high pressure inside. So now is a great time to pause for any questions you might have about these few experiments. I do have one last one, and this one is a true experiment. So we've talked about our Mentos and Coke experiment in the past, or we've performed this one here on Echo as a demonstration. But to really turn it into an experiment, we're going to be testing some different variables. We'll test some different types of items that we could drop into the Coke and see what kind of effects that we get. So if you do have any questions, please send them in the chat. If you have any questions about the Mentos and Diet Coke experiment that you might like me to address as we move through it, send those in the chat as well. As always, we want to thank our sponsors like the DTE Energy Foundation, like Denso, and our donors like you who are making donations to the Michigan Science Center at this time. We are very, very appreciative so that we can keep providing these Echo Live programs every weekday at 2:30 p.m. for everyone who is at home and looking for some science that they can try at home. And also, of course, the science that we can't try at home because maybe it's a little bit too dangerous, but we're happy to do that part for you. All right, let's take a look here. Let's see if we have any questions in our chat. Not seeing any on Facebook just yet. That's totally fine because we still have a whole nother experiment to try. All right, so we're going to be repeating our Mentos and Coke experiment, but this time we're going to manipulate the variables. So we talked about Mentos and Coke, but we actually haven't done Mentos and Coke so far. We've done Mentos and salt, and we've talked about how this reaction is a physical reaction, not a chemical reaction, but there's a lot of misconceptions about this experiment on the internet. Someone asked me to squeeze out the big straw, so I am going to do that so we can actually use this for something during this experiment. So there are a few misconceptions about the Mentos and Coke experiment. Some people tell us that it's the sugar in the Mentos that reacts with the sugarless or artificial sugar in the Diet Coke, which causes this crazy chemical reaction, thus creating a big pile of bubbles and making the Diet Coke turn into a geyser. Others tell us that this is a physical reaction. And we've talked about this on Echo in the past about how Mentos are covered in tiny little pores or tiny little dents that we call nucleation sites. So I have a picture here. So if you've ever stuck your finger or maybe even a straw into a beverage that is carbonated, right, we know that bubbles start to form on the surface of that object. So on your finger or on a straw, right, even though we may not be able to see little dents and little divots, it's easier to see on your fingers than on a straw, they are there. And so in this reaction, we say that these carbon dioxide bubbles, all they really need is something to attach to in order to be released from the liquid they're suspended in. So we say that all the bubbles will then attach to those little tiny microscopic dots, which we call nucleation sites, and then they quickly rush out of your Diet Coke, giving you a pretty cool reaction. So what we're going to be testing today is those two theories. Is it the nucleation sites or is it the sugar that causes this Mentos and Coke reaction to be so much fun? I'm going to set my egg experiment over to the side. Get that one out of the way because we know this experiment can be a little bit messy. So I've got my Skittles that I'm saving for later for kind of a mystery snack. And for this one, I've got a bunch of smaller bottles of Diet Coke. All right, so we'll set up our trays here. We've seen this one in the past. We know it can be a little bit messy. Make sure we scoot everything off to the side and out of the way. All right. So the important part in any experiment is that we're only changing one variable at a time. So you'll notice that all of these bottles of Diet Coke are identical. So if you'd like to do this experiment at home and change a different variable, you could experiment trying different brands or different types of carbonated drinks. All right, so we're going to uncap 2 of these bottles and we'll make a comparison. Now, if you were theorizing that it is the sugar in this reaction that creates the geyser, right, that's one we'll test first. So I've done the research, and before this program, I found out that there is an equal amount or gram weight of sugar in 2 of these gummy worms that I made earlier as in 2 of these Mentos mints. So what we'll do is we'll make sure it's our camera here. That way we can see our reactions. We're going to drop them in at the exact same time, and then we'll see which gives us a bigger reaction. I'm actually going to switch my hands. So we've got Mentos in this one here, Mentos in the center, towards the center of the table, and our gummy worms on the side. So here we go in 3, 2, 1. We can see that even though the sugar content was about the same by weight, right? We had a much more quick reaction in our Mentos and Coke reaction than with our gummy worms, right? So if you think about the texture of a gummy worm, they're a lot smoother, right? So maybe that gets a little bit of insight into our next experiment. So we'll open up 2 more bottles of Diet Coke, 1 here and 1 here. And this time, we can test something else. So I thought for this one, we might test these Skittles, which have about the same sugar content, again, as Mentos, maybe a bit smoother. But if you really, really look closely at a Skittle, they also are a little bit porous or a little bit rough. So let's go ahead with our next Mentos and Coke experiment. So again, Mentos over here, Skittles over here in 3, 2, 1. And we see a small amount of reaction happening, right? Even though the sugar content is about the same as our gummy worms, right? But these, we said, are more porous. So our very last experiment we're going to try, right, is between 2 porous substances. So we've got 2 more bottles of Diet Coke. Again, that variable will be unchanged. So we'll set these off to the side. We'll move our original experiments out of the way. And a good way, if you were to try this at home, right? A good way, even if you can't necessarily measure how high the geyser goes, right, is you can measure the amount of liquid left over after your experiment. So we can see that after our gummy worms, we've got almost a complete bottle of Diet Coke. With the Mentos, we've got a little bit less. For consistency, we can see that both of the Mentos had about the same amount of reaction. And then this one was our Skittles. And our Skittles reaction comes just to the top of that red line on the bottle. All right, so for our last reaction, we'll be comparing the effects of Mentos and salt. So we've done Mentos and salt, or we've done Diet Coke and salt before, but now we get to compare it to our Mentos reaction. So again, Mentos on this side here towards the center of the table, and I've loaded up our salt just into this little white tube so I can dump it all in at once. Same mass by weight, and let's see which one gives us a bigger reaction. Here we go in 3, 2, 1. So this one turned out a little interesting, right? So even though this reaction certainly went faster and much higher, we've lost approximately the same amount of liquid out of the bottle at the very end. So if we hold these two up, that one's still kind of leaking. We've got approximately the same amount left, right? So the Mentos really have that ideal texture to them. They're nucleated on all sides, which allow all those bubbles to really attach to their surface and be carried out of our reaction. Now, I said that I had kind of a special surprise as our very last experiment of the day. So I do have a video that I recorded just before our program outside. So if you were to try this experiment, I highly recommend doing it outside, especially if you're using larger bottles of your Coke here. And so we're going to try something on a larger scale, right? So now we've done our research, we've looked into our variables. We're sure that now we are testing, or what we want is that really heavily nucleated substance to pour inside. So we'll test one new substance, something that is even more nucleated than salt, and we'll compare it to our Coke geyser. So here we go with our very last experiment of the day. And I've got a video to show you. Here it is. All right, everybody, we've done our small scale experiments with our Mentos and Coke experiment. Now we're gonna make it big. So we've got 2-liter bottles of Diet Coke behind us. We'll be doing 2 different variables here. We've got Mentos on the left, and we have kitty litter on the right. So let's see which one makes the biggest geyser in our large scale version of our soda geyser experiment. Here we go. All right, we've got our 2 experiments ready to go in 3, 2, 1. So you can see that we had a clear winner. The Mentos are ideally designed for this experiment. They really trap onto those carbon dioxide molecules. They really shoot them out the top. Again, we really recommend that you try this one at home. Maybe try using a different brand of soda and tell us what kind of results you get. If you can think of another very porous kind of substance that you might like to experiment with, tell us about your results. Tell us about your experiment, what variables you chose to change in comparison to ours, and what kind of results you got. Were they the same? Were they different depending on the Coke that you use, or depending on the different objects you put inside? So we are just about out of time here. Someone asked, why does Diet Coke work better than the original? And I do have an answer for that. This is something that you can certainly test at home, but there is an answer to that question. Now, this is not about the sugar, but what we actually get when we use aspartame, which is the artificial sweetener that we use in Diet Cola, instead of using real sugar, is that we're actually able to super saturate the solution with gases. So since you are able to add so much more gas inside a bottle that has aspartame instead of real sugar, right, there's just more gas that's able to be released from that solution. Which one went higher? The answer was the Mentos. The other substance we tried in that reaction was kitty litter, which is highly, highly porous, but it really settles to the bottom very quickly. And since it's so small, the Mentos just work better because you're able to completely cover the surface with bubbles. So we'll be posting all of our streams from Echo Live on our YouTube channel. As always, if you are enjoying our streams, make sure that you are liking and following the Michigan Science Center Facebook page so that you're aware when they're going to go live every single day. Make sure that you share them on your wall for other families who might be interested. And if you're looking for the guides for all of these experiments and the other ones that we've talked about on Echo Live so far, this website right down here at the bottom, mysci.org/@home-science. That's where you can find activity guides for all of our candy chemistry experiments, for the egg in the bottle experiment, and for all the other ones we've talked about so far. So thank you everyone for joining us here for another episode of Echo Live. We hope we'll see you back here on Monday at 2:30 p.m. Eastern. Have a great rest of your day.